My name is Steve Nelson. I've been helping code mentor with both FRC teams for the last couple of years and then FTC teams, leading those coding there. Been doing Java for probably 20 years now, so this is kind of the standard that I deal with every day. So. Okay, so does everybody, there's flash drives that are going around the room?
Did everybody get them?
No.
Who has the flash drive?
Got one right now.
Okay, so you're copying. So just keep on moving them around the room. What we'll do is we'll go through this presentation and then we'll take breaks as we go through it. But we're going to get to a point where we want to actually have Eclipse and then run through Eclipse and just do some test programming, some of the basic state machines. Lindsay will go through that. So does everybody have Eclipse installed? Okay, so that's the main thing. As long as you have Eclipse installed, then everything should work from there. So, all right, so we're going to go through this slideshow.
Excuse me, before you start,
Yeah.
you're going through state machines, are you going to touch on command-based programming?
We'll do state machines that you can do a command-based type programming with state machines, but I don't necessarily call it that. So,
Okay, well, I know, the state
Yeah.
machine looks a lot like it.
yes, yes.
But, okay, because last year we programmed in command and kind of liked it.
Okay, okay. Yeah, this is one approach. There's a lot of different approaches for programming. I just find that this works quite well with control systems and managing your loops and everything.
Okay.
So we'll go through this. There's a lot of people, that present command-based programming. I've looked at it a little bit. It's very similar in terms of the final effect. So, okay. All right, so we're going to make Gabrielle do the introduction, the background here.
All right. So we're going to go over, obviously, the FRC Java programming, and then we're going to talk a little bit about dashboards, and then some about vision processing. All right, so this is a little background about us. In 2015, for our FTC competition, we had an Auton, and it used OpenCVC with the Android robot controller. And we found out there was a lot of problems with lighting, and that would really affect your Auton. And then in 2016...
Now let's go back to that. Tell them that we use Android phones, right?
Yeah.
We're doing Java.
We coded on phones.
Yes.
Okay, so what the thing with FTC is they're using two phones as their robot controller, and that was the year they made the switch. And we were using the actual phone on the camera and running the OpenCV library on that phone.
All right. Is that all?
That's good.
And then last year for FRC, we used USB camera,
Yeah.
and then we filtered it through to OpenCV's.
We did off-board.
Yeah.
So we did the OpenCV processing on the driver's station.
I didn't get time to study. I would like to point that out. All right. And then it worked for the most part. It was 80% successful, but we still have improvements that we can make. And then this year for FTC, we have a really successful Auton. We're still using the Android phones and OpenCV.
We improved the lighting.
Yeah, we figured out lighting, so that's good. And then for FRC this year, we are hoping to do an onboard module using Raspberry Pi and USB cams, multiple USB cams, other things.
The reason we want to do that is so we can get rid of the off-board processing issues, because more likely, if it's on the actual robot, it will be able to process faster.
Are you?
Well, potentially. One of the big issues with off-board processing was the networking. There's too much latency, and the drivers wouldn't use it because they thought it was too slow. So it could line up and target, but it was, you know, delayed, and they didn't like it. So this year, we're looking at onboard vision processing.
You said multiple cameras. Are you doing that for stereo or for something else?
No, multiple views.
Okay.
So let's say you have your shooter on one
Sure.
side and your intake on the other. So you could have an auto pickup and an auto shooter.
All right, and then for All right, I'll just hope I'm loud enough. Okay, so we recorded all of our images on our Android phones for FTC. We had to target a beacon, so basically we would try to find it using hue, saturation, and value filters. So we would find it and then figure out which color was which and go to it. All right. And then for the FRC competition last year, it was a weird target. It was a U shape, so we actually used that to our advantage with the reflective tape. So we were able to tell our code, this is the target if it fits these criteria, like having a U shape and being a certain brightness. And then we have different ones for long and short shot
Yeah, we have different settings.
settings. All right. Then this year for FTC, they used the same beacons, and then we were able to improve the beacon targeting.
Yeah.
And then we log our data so we know what the problem is, most likely. Yeah.
Here.
Okay, so a tool we use a lot in FTC and FRC is called data plot. And basically, we're printing out these values in order to see what was wrong. For example, at our last competition for our FTC robotics, we thought one of our sensors went bad. We thought our gyro went bad because the autonomous wasn't working. But then when we had time to go through it and go through the data plots, we actually figured out our gyro and our sonar sensor were not working, and we ended up replacing the module it was connected to for wiring, and that fixed all of our problems. The actual sensors weren't broken. So they weren't reading any values, and that's how we knew something's wrong besides just the sensors, because we didn't change any of our code. It's nice because we set headings and targets. Like for example, for our gyro, we set a target we wanted to like turn to, how much we wanted to turn, and then we see how much the gyro is actually turning. Okay. So we code in state machines for our autonomous, and we print out our state values so we know what sensor is doing what in each state, so we can make sure it's doing the right thing. And then
These are also counters for the time it sees the beacon.
okay, so we have a count, and that's how we kind of like keep track of time in our state machine, so that sees how long it saw the beacon for FTC, and then the last graph up there is distance, and it's showing like how far away it is and what our sensors are reading, and the closer they are, then we know we're at the beacon, so we should press the button.
So the pink is the sonar. So if you look here, the pink is the sonar sensor output. Okay, so it gets smaller as you get closer. Okay, so it gets smaller as you get closer. The blue line is actually the camera. So we're actually using the camera to look at the width of the beacon. So as we get closer, it gets wider. Okay. So it's actually, the camera has a nice clean signal of how close you're getting to that beacon object. So basically you can fuse two sensors together. You can use the sonar and the camera, and then you can basically set a threshold. So if one goes bad, you can use the other one. So the camera has a lot of capabilities of using it as a range sensor as well.
No, it's
Looking at it.
yeah, thanks. Okay, so the lessons we learned was with our color filter configuration, we set our RGB and our HSV values. We had to play around with them a little bit using grip. Are we showing that now?
We'll show it.
Okay, we'll show that later on in our presentation. And then we changed our exposure because of the variable lighting conditions, because they're different like at every single competition you go to, every single building, the lighting's going to be different. So we're eliminating that error by changing our exposure on our camera. And then the target, oh, okay. So we added logic to make sure it was the right target. For example, in FTC, one of our logs, one of our pictures had a little glimpse of a volunteer shirt because it was similar to red, and then it had the red beacon over in the corner, and we put constraints on it, so it's like, well, it has to be this big in order to say, oh, that's a beacon, not a person, so it won't go and target the
Or
person.
the red and blue have to be close together.
Oh yeah, and with the beacons, it has red and blue next to each other, so we also have the logic that if red and blue is right next to each other, then that's a beacon. So the robot will know which target to go for.
The other thing is also for FRC last year, the U shape, we actually take and we say there's a rectangle. If there's data that shows up in that rectangle, that passes, but then we put another rectangle inside of it and says there can't be any data in that rectangle. So that lets us detect a U shape. So we'll get to that when we look at OpenCV and grip, but it gives you the capability of anything we detect, we can zoom in and kind of refine that shape. Okay. All right.
Okay, so for testing, we log our data all the time, and we use a data logger, which I showed you earlier, which we make our graphs on, which is a very helpful tool. And then we also save the images from our phone to a file so we can see through the images what the robot's actually seeing on the field to see if it's going in the direct direction. Okay, so we're using closed loop controls on vision. What? Oh, question.
So when you're saving the images for video, are you saving that on the phone?
Yes. We just save the images directly to the phone, and then we can plug the phone into the computer and see it.
And then on FRC, we save it on the driver's station. We record all the images from the match on the driver's station.
You want to help that?
Yeah, so closed loop control with vision. The one thing that, and other teams are doing this, at Worlds, they presented on it, but basically, you don't want to close loop control directly from your images from your camera, because there could be latency, you may not get the update rate that you want. So what we do is, we use the camera to kind of triangulate where the target is, okay? And then, once it triangulates where the target is, we adjust the beacon heading to where we want to go. So we don't close loop control directly on the camera image, we close loop control on the gyroscope, the heading that we want the robot to take. So if we see the target over to the right, we say we need to turn 30 degrees to the right. And then we close loop control on the gyro to make the robot turn 30 degrees to the right, okay? So if your camera ever goes down, which actually the camera seems more reliable than the gyro, if your camera did go down or it got delayed for some reason, the robot would just follow that heading that it's currently targeting, okay?
Finger there.
Put your finger here. I don't know what.
So I'm gonna.
Yeah.
Alright, I'm gonna go over like the basics to programming and how we code object-oriented. So the first step is to having Eclipse installed.
Yeah,
Oh, and also you should have the WPI lib installed on your computer.
Well, you raise your hands if you have.
Did everybody get the flash drive?
Okay. Does everybody has Eclipse, right? Has everybody gone through and installed the WPI lib component? Okay, so those are the main two things.
Alright, and then next we're gonna create some classes, and that's where you're gonna be doing your coding. And then you're gonna code your program through Java, and then you're gonna download your code to the robot and test it. Okay, so we code object-oriented, which means we organized our projects based on classes. So first we have a package, which is made up of multiple classes, and then we have multiple classes inside that package. That's where you program the code. For example, like you could have a drivetrain class, and you can have like an ARM class. And then also we do methods. So methods are things you can program an object to do. And we have strings, usually for printing out our values to see which sensors, which value. And then there's also integer, which is just, the types of variables are integer, a double, which is with a decimal point, and a float, which is a decimal point also.
Why is this? Just like in the same spot, it doesn't like to move.
So there's some examples right there. So basically that's just the basics to Java programming. Integers are number, negative, it's like from 1 or like 25. A double has a decimal point in it, so usually we use that for our motors when we're controlling our motors. If you want to set it to 0, you're actually going to set it to 0.0 because it's a double. And then there's strings, so you can print out a line saying like your gyro value is, and then you can print out your gyro value.
Yeah, so this is just a link to the Oracle docs, so if you want to go in and read up on object-oriented coding, what's an object, what's a class, what are the packages, there's some good tutorials on that. We're not going to go through all the details of that here, but there's a reference there. Okay, so how many of you know what feedback or closed-loop controls are? Okay, so quite a few of you
How
have
many
a...
don't, I guess is the other question.
Yeah, how many don't know what a closed-loop control means? Okay. So one analogy is steering a ship, okay? Or driving a car down the highway on the lanes. But steering a ship is more closed-loop control. So if you're steering a ship in rough water, right, you have to control the rudder. Okay, you're going to turn it to the right if you want to go left. If you want to go left, you got to turn it right. You controlling that rudder is closed-loop control based on the heading you want to take. Okay, so how it basically works is you have a target, which is your heading. You have an error, which is your actual heading, and then you have a controller, which is your arm, and then the command is going to go back to the rudder, and then this is not working. Okay, so then you feed back. Your command is feeding back into the ship you're steering. Okay, so it's basically the same thing with the robot. You have a heading, and you're going to put power, plus or minus power to your left and your right wheels to steer it in the right heading. Okay, so does anybody know what kind of controller is most commonly used?
PID.
PID controllers. Okay, who knows what the P stands for? Proportional. So what does that mean? If I have an error of, if I have a proportional gain of 1 and my error is 10 degrees, what's the output gonna be?
10 degrees and counts here.
Well, negative 10 probably, right? Because it's usually negative feedback. So if your gain is 1, it's gonna give the 1 times your error as feedback. What if your gain is 0.5? gonna give 5 degrees of feedback, okay? So that's your proportional. So proportional is directly proportional to the error. That's the feedback that you get. What's the next one? What's the high? Integral, okay? Integral is adding up your error over time, okay? So if I'm driving or if I'm steering a ship for 10 minutes and I wander off course by 10 degrees, it's going to then slowly add 10 degrees feedback to try to get me back on course, okay? So the problem with integral though is you can have wind-up, so it may throw you back on course, but then it may throw you off course the other way, okay? So when you're doing PID, you start off with the proportional, and then depending on what you're trying to control, you may want to have integral, you may not, okay? What's the next one? Derivative, okay? So who can think of what the derivative does?
Changes based on how fast you're approaching the target.
Yep, so if you're coming in too hot, it tries to slow you down. If you're coming in too slow, it tries to speed you up. Okay? So it's a nice adjustment. So if you have a robot, or if you're trying to steer to a heading and your robot does this, it kind of seeks. If you add derivative, it will make that seeking a lot less. Okay? Because what it's doing is it's overshooting each way. Derivative will compensate for that overshoot and try to focus you in tighter. Okay? So a lot of, at least from what I've seen, a lot of the controls with headings, you usually do a PD controller. You usually don't need the I term, okay? Unless you want to get down to that, millimeter position, you really don't need the I. So with, if you're controlling the heading with motors and steering the robot, you put a PD controller on your motors, okay? Who knows what an open loop system is? Yeah.
You give it a command and just leave it there.
Yep. So if you code off on and you say, I want the motor at 50% power for 3 seconds, that's open loop, okay? So, and it works quite well with robotics. It's going to get you 80% there, right? You can say 50% power for 3 seconds, and put power to turn the robot for 2 seconds, and then go straight again. The problem is, who can tell me what variable would affect that?
Battery.
Battery voltage, right?
Carpet, wheel traction.
Yep. Yeah, friction, something
Yep.
changes. But the number one thing that changes the most that I've seen is the battery voltage, right? You go into a competition, you think you have a good charge battery, it's 14 volts, all time works great. Next round you go in and you have a 12-volt battery, and it doesn't quite go as far, or it doesn't turn as much. That's an issue with open loop controls.
Yeah. Actually, we've seen more problems with differential frictions of one drive set from drives from one side to the other.
That too,
The
yeah. But that should be
gearboxes.
consistent from,
Well, yeah, it's consistent. You can
Consistently
you can
wrong.
plan for it.
Yeah.
Sort of consistent.
yeah. So, because even if you have a gyro that drifts, if it consistently drifts, you can
Yes.
account for that. If I turn 90 degrees, it's actually 80. I don't care as long as it does the same thing, right? So the problem is when you throw in that variable that throws everything off, and that's usually the battery, from what I've seen. So, okay. So there's terminology for closed loop controls, but the one where it jumps over, that's what? Overshooting, okay? And then if you're too slow, it's undershooting. Depending on what you're trying to do, some overshoot is good, some undershoot is good. You just don't want it to be wild and crazy, okay? So that's kind of the controls. There are other type of control systems that get a lot more complicated. There's state space control systems. You can model and simulate your whole environment. It gets pretty complicated. You can get degrees focused specifically on those areas of control. A new area that people are getting into is adaptive or autonomous control. neural networks where it's all machine intelligence, where they basically feed it all the data and it figures out how to control the output. So rather than coding up a PID controller, you got to record all your data for what you want it to do, and then you feed it into machine learning, and it will basically mimic how you want it to perform, and then it will output and control your motor. So there's a lot of different things.
Okay, so the way we control these overshoot and undershoot is adjusting the gains, and adjusting the gains is called tuning. Usually you have to do a lot of experimenting with it, kind of change it a little bit at a time, don't change it too drastically, but it does take some trial and error to see what works best on your robot. Okay, so, alright, so,
When you did trial and error, did you redeploy for each time?
yes. When you're making a change to like the gain, we redeployed it each time, and then tested it out, and then we're like, oh, well, this isn't the right value, so then we had to go back, change it in the code, redeploy it.
Have you ever thought of other options rather than redeploying each time?
One way I've seen teams do it is sometimes they'll program a couple of buttons in the controller that can increment like the, each of the terms by like 0.01.
I think the driver stations.
Yeah, the smart dashboard you can
Yeah,
set up.
You can use Smart Dashboard for doing that, so if you actually tied your PID parameters on the Smart Dashboard, then the robot would read them off of there. You know, it depends on what you want to do. But Smart Dashboard, if you're going to do a lot of calibration, I would probably recommend that versus redeploying all the time. We didn't really have to change ours that much.
Not too much
Yeah.
this season. Alright, so now we're gonna talk about state machines. They aren't that complicated. They're actually very helpful for, even if a person's not a programmer, to see what the robot's supposed to do. So, the reason we use them is because they're pretty easy to follow and they're easy to debug, because you can tell like if your robot's stuck in a certain state when you print out the state to see how it's going and make sure it keeps on going from the next state to the next state and doesn't skip any. They're pretty organized. It's a step-by-step procedure, and when programmers start, they usually start with pseudocode, like say I want to go forward, backwards, turn right, and then turn left. Those are each going to be a separate state, so state 1's going to be move forward. It's a step-by-step procedure, and then usually there are conditions leading on to the next state. Usually we put our sensors to use there and set some thresholds or ranges the sensor values need to be in order to go on to the next state. Alright, so are we going to start the state machine now or not? How many people have coded with the state machine before, or switch statement? They're called the same.
It's all few of you. Okay. So we're thinking of going through an example here and actually code it. It's not a real robot, it's just a little simulation program. So what we're going to do is do a little simulation here. So how do we start with the state machine? We have to have Java classes, right? We have to have a test program, okay? So on your file, on that drive, there is a folder called source state machine example.zip. So if you extract that, and what we're going to do is we're going to pull that into Eclipse as a project. What it has is it has basically 5 classes in that package. Okay? So we'll talk about it real quick, then we'll show a laptop here and we'll run through it. But basically there's a main. So in Java, you have to run a main program, okay? And then that main program is actually, in this case, it's drawing a graphic on the screen, okay? So it's calling this paint method, all right? When you're doing graphics, you have to periodically display the screen, and that's where we have a thread. So who knows what a thread is? Who can explain what a thread is? Good.
A thread is a process on a machine, so it's like a sub-program. It'll execute apart from your main program.
me give you so, working with data, as an example, you frequently have computers that are capable of doing multiple things at the same time. And you'll hear that as being called multi-thread. So the computers that we have today are multi-threaded. When you're running your Outlook or mail program next to your Word program, each one of those is running in their own thread and actually maybe running multiple threads underneath itself. And keeping track of all of that is one of the things that makes a good threaded program.
So yeah, so threading, you basically, your CPU can give a time slice to different programs. So I can have one program that can launch 100 threads, okay? And then the CPU is gonna give a little time slice to each thread, and it's gonna execute some code. But they're all running in parallel, right? All these programs are running in parallel with their thread. Multi-threading is good, but it adds some issues as well. You have to, there's ways of keeping things in sync, and you don't want to starve one thread and have one thread try to consume all the resources. So
Here's a question for, how many cores does a RoboVio have? So if you think of a core, in this particular case, how many threads can the RoboVio run at a time?
We can run two at the same time, but you can have any
Exactly.
number of threads.
yeah, yeah. So when you're doing time slices, so you actually have two CPUs, and they're given a time slice to each thread, so you can have two threads executing code at the same time. So,
You have four, somebody's getting started.
yep, yep. Or if you have a four-core system, like an Android phone or whatever, it can run 4 threads at the same time. So if you ever look at Android and you ever look at the logs, there's all kinds of things running on Android. They're all taking threads, they're running on their own threads, and it does a pretty good job of isolating your applications, letting them run, and letting them all run in parallel, right? It'd be a pain to open up an app, then you'd have to kill it to run another app, then you'd have to kill that to run another app. That's why they do threading. Okay. All right, so there's a thread that updates the UI. Then there's a all-time class. That's what we're gonna change as we go through this. And then there's a little Android. This is just a class to represent the little Android figure that's on the screen.
So what we're gonna have you do is we're gonna have a little Android man, and you're gonna move it around in a box, and then you're gonna move it around through an obstacle course, and we're gonna see how far you guys can get.
Okay. So we'll take some time and try to do this, see if it works out, if everybody is interested in doing that. We also have it where it records. So naturally, there's a class that creates a MJPEG file from this run that you'll do. So you can look at a video of what it does, okay? So these are the classes, they're on that file. First thing we want to do is do a square path, okay? So we're gonna make it go from one position to the next, and then on to the next, okay? Yeah, so we're actually, what we'll do is because it's already on this laptop, we can, we'll do it on this one, so we show you importing the folder. So everybody, if you have Eclipse, make sure you unzip that folder.
And we opened the state machine example.
After unzipping it.
After unzipping it, so did you guys get all unzipped?
Yes.
Okay, so then you just drag it over like this,
Drag it into source.
and you drag it into source.
Okay, did everybody create a new project in Eclipse? Okay,
Yeah.
so that works. So go file, new,
Okay,
So go like file new, and then Java.
Java project.
okay.
And then you can name it like state machine test. And then you can open up your folder view,
Well, no, first expand it. Okay, so expand out state machine test, you should see a folder here called source, SRC, source.
And then what you're gonna do is, you're gonna open your,
File browser.
file browser, and then you're just gonna click and hold and drag that into there.
So you're gonna have two folders. So there'll be folders in your file view, and then you'll drag them into here under source, and they're actually called packages in Java. A package is really just a folder. Okay? It's a way of organizing your files.
Oh, wait.
Okay? All right? So if everybody has this, so now we have a folder here. It has a class for the Android, it has a class for Auton, it has a class for the GUI main, and then for the thread. So open up GUI main, so just double click on it. Okay? So this is just gonna launch the application. Okay? So go up and hit the play or the green button. Okay, we gotta do one more thing.
Why do this picture well?
You know what? I don't think we should have.
Not on there?
May have forgotten to copy the graphics file. That would be a problem.
Yeah. You need to have the archive again?
Do that, or if you put it like on Dropbox or something, the Wi-Fi, it seems okay.
Is instead of drawing the image, we're gonna just draw a circle. Okay, so everybody go to your Android class. Okay, and there'll be a method. This is the Android class. And this is basically what manages drawing. It draws a little image of an Android on the screen. Well, we forgot the image file for Android. So go down to line 39. We're going to comment out where it draws the image, and we're going to draw a circle. So go in there, like G2.
You guys are way ahead.
Lost our Android guy.
On Android.
All right, we'll get the Android back in a minute. Okay, so one line of code to change. Can everybody see this? So, everybody, if you see the file, open up your Android.java class. It'll pop up in the middle here, go to line 40, or line 39. Comment out line 39, and then add this line.
They can't see it.
A little
You're
small
gonna
to
have to
see.
say it. There's no way to zoom these things. The projector's going to.
I can see it.
Yeah, maybe visible.
I was there.
Put in nice notes at it, you know, like.
IntelliJ has a nice presentation.
Or you could use the magnifier tool, it's under accessibility or accessories or
That sounds
something.
good.
They're gonna comment out the other one and then replace it.
Comment out 39, put that on hold.
Okay, so it goes one way for a certain amount of time, then it turns and goes another way, right? So it's 0 degrees, and then it goes 90 degrees, okay? And some of yours may run faster or slower than this, okay? Based on your processing. All right, so now, is everybody good to move on to the next step?
No.
Okay. This is a method, draw a rectangle, and then you're given it the coordinates on the screen, the x and the y coordinates, and the width and the height, so that it will draw the rectangle on the screen. Okay. We can probably even draw a fill rectangle, but we'll ignore that for now. Okay.
Why would it be unable to run? We'll run it.
We'll run it. Okay, we'll look at that in a second. Okay, so the next thing is, open up the class. There's a class called Auton, and then there's a state machine that will go. So why don't you walk through here? Let's put it on. See how it works. Yes.
Okay, so in your on-time class, you're gonna have the public voice process, and inside that, we're gonna go to our state machine. So, the first logic is basically saying if it's not running, what we're gonna do is set our next state equal to state. So, in the beginning, we made variables called state, next state, and state count. So what state does is it just keeps track of what states it's in. Next state allows it to go to the next state after the state it's in. And then the state count is for how long you're in each state. So so what you're doing in a state machine is running a switch statement. So the variable you're switching is actually the state, so you're changing the state every time your conditions say next state equals, you're changing the state every time. With state machines and the actual switch statement, they're called cases, but when we're talking about it like out loud, we always say state. I don't know why they're case, it's just how it is. And when you're coding in state machines, always make sure you have a break after every case. If you don't, then you'll run into issues and it won't follow the order it's supposed to. So in the first case, case 0, it's saying if the state count is greater than 10, so that's for a certain amount of time, it's gonna put the Android guy at the X point of 300, the Y point of 300, and then it's gonna set its velocity, which is its speed, to 6. And then this next state equals 1 right here, that's allowing it to go to case 1. Does that make sense? And then case 1 is saying if the state count is greater than 50, we're going to set the heading equal to 90. So we're going to turn it 90 degrees. And then it's going to go to the next state. Case 2 after that is saying for the same amount of time, so if the state count is greater than 50, it's going to go to 200. And the 200 case is actually going to wait there for 200 counts, and then it's going to go back to state 0. So then it's going to do the same thing again. And then we have this logic at the bottom here. So we have this logic at the bottom of your state machine, and what that's doing is it's saying if next state's not equal to the actual state, then it's gonna reset the state count, it's gonna set the state equal to next state. So we'll actually keep going through all the states. And if that's not true and everything's going correctly, we're just gonna keep incrementing our incrementing our state count, which will allow us to keep going through the process of these states. Is there any questions on that? Yeah.
On state two, you were checking the same condition as state one, why didn't you put that, what if you did it in case two in the case one part, in heading?
Okay, the reason we keep it separate is because basically it's like a step-by-step procedure. So in case one, we're actually turning 90 degrees, but in case two, we're just waiting for a certain amount of time and then going on to the next station. So it's actually going to be stepped. It's not going to be doing it. What else should I go through then?
Okay, hang on one second. No, the runtime, it won't run the program. There's a runtime.
So how about you guys add a case 3 for it to turn not to the right but to the left after case 2.
Yep, and then we could.
Thinking about it. If this is true, then you do steps. That's what, if you look up there, that's what it's talking about there. If something, a certain number, if it's greater than 50, once you understand the code, it's actually pretty
A lot of people are having Eclipse. There may be issues with Eclipse where you go to do run as. It's not set up right to run as an application. We'll try to work through those. And then in the meantime, people who have it running, while you try to move on to make it go around in a square, okay? All right? So if this is how the state machine works, so basically state 0 resets the location of the box on the screen, and then it sets a velocity, okay? So now the current velocity is going to be on your current heading, okay? So right now the heading starts off at 0. So what it's going to do is it's going to travel on a heading of 0 at a velocity of 6 pixels per loop until state count goes over 50. And then what it's going to do is it's going to change the heading, okay? So the thing to do next is create a case in case 2, change the heading. If we wanted to rotate back the other way, what should we change the heading to? From 90 to 180, okay? So we want to change the heading to 180, and then we want to change the heading to what? To go back and make a square. So 90, 180, 270, okay? So if you put in the same time for the state count, it should make a complete square, okay? So that's one way to do it. Another way, instead of using time, we can actually use the position, okay? So you could say get the X position, if it's greater than 300, then change the heading, okay? So we'll go through those 2 scenarios, all right? And then we'll try to work around, if people have problems with Eclipse, we'll try to help work through that. So if you haven't run it, play around with that, try adding another state to make it turn again, okay? the position of the rectangle. So we have to, in the Android class, you're gonna have to add public to, no, it's not void, it's public in. You're gonna have to add two methods. Public in, who can tell me what they think the first method would be? Get, that's, yeah. Okay, and then what is that gonna return? No pressure. Then you're gonna return this dot. Yep. Okay. Okay, now there's a problem with that, because that type is a double, so we have to cast it to an int. Remember how to cast? Okay, so this will actually, it may be hard to see, but we're casting the double to an integer when we return the position. Okay, so now do it for the y. Okay, so now, save that, because this doesn't auto save like in your studio. Okay. So this lets us access the variables within that object. Okay. Okay, so now what we're going to do is we're going to go into our Auton class, and you're going to say on the first, instead of state count, we're going to switch that to if Android dot get. If that's greater than 300, then we're going to turn. Okay? So that's basically, and then change that to Android dot get y greater than. Now, the thing with this is going to be more precise. So now, even though everybody's laptop runs at different speeds, this is going to wind up putting you in the same position. So now, next stage, make that 3, and change the heading to 180. Nope, make that 90. Put a line, add a line. Android data set heading. And then we're going to add another case to turn again. One thing with cases, make sure you use your break. Make sure you put that break in there, because what it will do is it will fall down to the next case. That is going to be less than 100.
Where the coin is.
Because you're starting at 200. So the first two distances are gonna be 600, and then the second two distances are gonna be 300.
Okay, so now if you guys have, if you know where your workspace is on Eclipse, under Kettering, wherever your folder is, so if everybody has your project, if you can look at, if you find your project on your drive, there'll be a folder for your state machine in your project. This program is going to generate an output file as an MJPEG, and then you can play it. Okay, and then it will play, and it creates a video for you of your results. Okay, so it's a nice little job utility that creates an MJPEG.
Okay, if you go that again, nobody's listening back here.
So if you go into your project,
You know, how do you do that?
in Eclipse, if you look at the directory where your project is, there will be a file called out.mjpeg. Play that in your media player and you'll see a video of what your program is doing.
Can you switch back to the program to show where you're getting the exponents?
If everybody looks at the code, state 0 places it in position 300, 300. Okay? So you start in position 300, 300. So you're making a square. So this is 300, 300.
Three, 300, 600.
Okay, so who has it working out position? All right, a couple of people? All right.
Do you need help with it?
Anybody need help?
There's a lot of pizza, you guys better be hungry. I'm the only one to fix
Follow up with you later. But what we're going to do is we're going to plot it, so you can see the values of your sensors and things like that. So the first thing you're going to do is, in the all-time class, where we define our variables, we're going to add a new variable called printWriter P. Okay, printWriter is a class that's built into the Java library. So we're going to create a new, we're going to include a printWriter class, and then we're going to do, then we're going to add this code here in. Yeah. Then we're going to add this code into the all-time state.
Make that bigger, right?
Yeah, we'll make this bigger. So what we're doing is we're creating a printWriter, and in the printWriter it takes the file output stream as its argument. And then the file output stream takes a log.csv as the file name. Okay? And then we're wrapping that with a try-catch block, because in Java, a lot of these methods, and when you create something, it throws an exception. Okay? So you can put a try-catch block around catching that exception. In this case, it does it will throw an exception like a file not found or something like that. Okay? So this code will then open up our stream to start writing to that file. This should overwrite whatever's there. It should not have been. It should automatically import, so you hit like Alt Enter.
I'm guessing.
If there's a red line under it, get the drop down and say import.
No, I could tell you.
That's what it's saying. Oh, do we have to do it separately as well?
So you have to create the new printWriter class. Okay.
Right.
And then what we're going to do is we're going to in our state machine, in our process method, we need to print out the header of the file.
I need my computer stopped in the midst of doing some updates earlier, so I don't know.
Oh, it's gotta be PR.
What's the class that you?
Okay, so this is going to print the line, the first line in the file. Print out time, that's in the Y. Okay, so we're going to print that out as the header of the file. And then what we're going to do that is we're going to print this out when it transitions from state 0 to state 1. Okay, so it will execute only one time. Okay, then what we're going to do is we're going to, as long as state is greater than 0, we're going to print out our data. Okay, so does everybody have the try-catch block yet?
Yeah, we have that.
Well, okay, so keep working on that. Okay, so we're gonna do this on, going from state 0 to state 1. Okay. And then we're gonna do this all the time. Okay. And then there's one last thing we have to do is we have to close the file, okay? So down in, when we go transition to say 200, wherever you transition to your end, you're just going to do a P dot close. It's within the if statement, so like here, I have if in my case 4, when I transition that state to 200, I just do P dot close. So this is how you can write your data to a log file. All one line. It could be 2 lines if you want. So now, once you have this in, try running it, and then check to see if it creates that log file. So you'll need it, so if it's red, you need to highlight where it's red, and then you drop down and there, just say import. So print writer and file output stream are classes.
It's getting a little loud. Shh. You guys, I can't hear this.
Make sure you see these at the top of your file. Okay, import java.io.file output stream and io.printwriter.
Do that, tell me. One Catholic school, St. John, you might want to join because they didn't get anything.
Okay.
So the only file for this was on that flash drive. So what we're going to do is we're going to open up this source file, and you can create your own comment delimited file and it will read it. Basically, we have to go navigate to where that file is located. And then the default for Eclipse is going to be a workspace folder. And then you're going to have your Kettering state machine, or state machine test is what we called it. And then you open up the log file, Okay, and then it's gonna show you a sample of the log file, and then you have to tell it the first row are your headings. So we say 1 for the first row, and then we import the data. And now the data is imported, so you can actually see all the data elements down here. But what we want to do is we want to plot our data. So we have to plot it as time on the bottom axis here. And then we can go add, we can add a data curve, and then we can select the X position. And then that will plot the X value over time, and then we can also plot the Y value. Okay? So that's your data from your simulation. Okay? So this helps to do that on the robot, so you can actually see what is your gyro reading, what state are you in, things like that. We could have added state to this log file too. That would probably be a good thing to add. Okay? So we use this tool a lot for looking at the data. You can use Excel if you want, but this tends to graph it and work better. You can add more graph panes, right? So I can add more plots. So it's a pretty good tool for doing that. Okay. And then the other thing is you can add an event line. So if I want to see the actual data values at different points in time, I can scroll along the time and see the values. So it works pretty well.
Now, where did you get this from?
It's online, and it's included in the flash drive. Okay. All right, so we're gonna switch back to the presentation. So homework, if anybody's interested, create an obstacle course and try to drive around the obstacle course, right, with your state machine. All right? So you could put obstacles at certain positions, and then you could start at one location and try to finish in another location. Okay? So next one, we can talk real quick about when you're doing the robot controls, you don't want to just put 100% power to a motor. You want to ramp your power, okay? So typically we have a state machine where we may have a state where we ramp up the power before we move on to the next value, okay? So usually setting a target and ramping to it is a function that we do a lot in the state machines, okay? You can also do like a smooth turn, right? We're doing an instant turn in the example. You could do a smooth turn by slowly changing your heading. Right, every loop you change your heading by 5 degrees. Okay. Logging, right? We kind of went through a little bit of the logging and how you can write that data to a file. It depends on the environment and if you can actually write the file and the permissions, but once you get it working, you can write the file out, then you can plot it. Okay. All right, I think we already did our break. We want to talk a little bit about, this is the FRC code from last year.
Okay, so, last year we coded like object-oriented interface. So, these are the examples of our classes. So we had, an auto driver controller, a controls interface, a heading controller, a drive controller, like a robot base and everything. So we kind of split each component of our robot up into different classes. So like for example, our catapult and our intake controller was in a separate class than our actual robot base.
Okay, so this is all on that file. This is all actually the source code from last year. Okay, so we had multiple Alcon state machine classes. We had, we tried to break it up as much as we could. So we could reuse
and Auton, so those are different state machines, so every new Auton state machine is a different version of Auton.
Now, the one advantage of doing this was we could reuse our auto target controller in both Taliap and Auton. Okay? So we didn't have to write it differently. Not extended. Yeah, go on. When you get into the controlling the actual robot, there's a class called Robot. What we did is we extended that with the robot base class. And basically you have autonomous method, you have the operator control method, you have the teleop init method. So what we did is we extended these and we have our loops running in those classes. And the loop runs constantly. So what we did is we put a sleep there every 1 millisecond, and then at every 20 milliseconds we run our code. Okay? So the one thing I found is with all these environments, their loop times, if you try to use their loop times, they're never consistent. Okay, so if you ever want to do any kind of controls or filtering or derivatives, you're going to have to use time in them and make them more complicated. So rather than that, what we do is we set our loop time to be constant. Okay, so we run at a 20 millisecond loop time. Okay, and that's in the example code there that shows how to do that. What's that?
One thing, you can run into problems with that if you set your loop time too short, because it might take longer than 20 milliseconds to run one iteration of your code.
Oh yeah.
So
Yeah.
sometimes the better way to handle that might be to have a static class variable that tracks what the last time the class was called.
Yeah, yeah, yeah. So actually, I think this tries to run every 20 milliseconds, and then it will just stack up. And it will, if one runs too quick, then that's one just gonna run after. Well, I'd have to look. Yeah, I think it, I'd have to look at the code, but yeah, I've done this different ways.
The WPI lib has a pretty good timer class in it too, that can loop it, iterate for you if you don't want to write it yourself.
Yeah, yeah, you can do timers, you can do different things. If you're doing a real-time control system, you'd use an interrupt, and then that would guarantee your timing, but there's no interrupts here, so. But, the key is do your best to get it on a consistent loop time. That way, when you do your gains,
I know that
they're constant.
I know the WPI library has both the iterative and the event-based model, and the event-based model might get a little bit closer to the interrupt programming.
Yeah, yeah, it may. There's a lot of different ways you can look at it. I just prefer to manage my own loop times and that stuff. That's just the way I like to do things. But I would check your logs. First thing you want to do is set up your base, log every loop, and log the timestamp. And make sure you're getting a consistent loop time. And that's really the key. Because if you don't log it, you'll never know. Okay? So that's what I focus on, is making sure you log it, see that you're getting a consistent loop time. Okay, so some lessons learned from last year. We made a couple mistakes with Auton. If you change Auton and it actually crashes, it tends to lock out your robot so it doesn't run teleop. So one easy way, at least the way it was programmed this way, wrap it with a try-catch block. So even if Auton fails, it's not going to crash teleop. Okay? So that was one item there. We created interfaces in Java so that we could reuse common code between teleop and Auton. Multiple robots. We actually had a test-based robot and a competition robot. We gave them different team numbers, and we made it so our code could be deployed on both robots without changing anything. So there's a little bit of logic that we had to add to do that, but it made it a lot simpler than trying to track 2 code bases. And then we had network issues in the competition at Worlds. Everything was working great at States. We had all time working really well. Go to Worlds and the camera wasn't working. So we were not using static IP addresses, which was a bad, that was our fault.
Yeah.
So we switched to using static IP addresses and
So
installed.
always use static.
Yep, yep. So. Dashboards. You want to talk about dashboards? Go through.
Alright, so,
Well, it's okay. So we developed a custom dashboard last year for FRC. Okay, it sits on top of the driver station controls, and we put our own camera view in there, and we put our own widgets for viewing different data elements. Okay, so we'll talk about the approach, maybe some of the widgets that we put in, the camera views and how those work, some of the controls, and then how we did communication to the robot. Okay. So this is a view, a snapshot of our dashboard. It's actually part of that flash drive. You can pull that file in and probably launch it. So we basically had indicators that would say what year we were in, what heading, we were doing auto heading. Our robot had some different driving modes. So you could go, shrink it down to get under the low bar, or, drive manually, or go into a pickup mode. So we could control those modes. We have a compass, so we had a heading. We had our target and our actual heading. And then we had a camera in the middle. We had an all-time selector on top. And then we had some variables on the right. So if we wanted to monitor pressure or various other items, we just print those out. So you could do smart dashboard and things like that, but we wanted to try to do our own custom dashboard. And it worked out pretty well. There's other dashboards that are made up out there, yeah. Yep. Okay, so if you want to build your own, there's a couple approaches you can take. You can do it in Java, which is what we use. There's actually like 3 or 4 different ways you can do it in Java. We just took the simplest approach. You can do HTML, so if you wanted to do a web page as your dashboard, you could do that as well. The only problem with HTML is now it's not as easy to integrate with some of the data, right? If I want to talk to network tables, I have to create my own server and do some of that, okay? So HTML is easier to render and lay it out, but Java is easier to integrate with everything, okay? You can do custom widgets. So we had a custom compass heading. We were working on some status bars for like the motor current. Our custom indicators, so you can do gauges. There's all kinds of libraries out there for doing gauges and things like that. So you can make it look like whatever you want. Okay, the camera view. So Java has a nice component where you can view the camera. But what we're running OpenCV as part of the dashboard, so we're just taking the output of OpenCV and presenting it on the screen, okay? So that's where we're doing our targeting, and then we can overlay and draw graphics on top of the camera image, okay? The problem with this from last year is the network bandwidth is limited, so the refresh rate of the camera was not the best, and it was somewhat delayed, so we lowered the resolution of the camera. That helped a bit, but still was too slow. So actually in the future, we're thinking for next season, not even showing the whole camera view, but just showing contours and sending them back to the drive station, and then also allowing to switch between multiple cameras. So we'll show on grip how you do the contours. Now, our indicators, our controls, you know, showing whether you're in high or low gear, what we did is the robot would write to network tables, and then the dashboard would listen to the network table and see if the variable is true or false, and then show the icon appropriately. So network tables is a real nice tool for passing data between the robot and the drive station. Yeah, so this is network tables. Works pretty well. Haven't had any issues with that. The only problem is they used to have a native Java version that they got rid of. So now you have a native compiled version for Windows and whatever. So in the future, we're actually looking at, we may do some WebSocket communication and try that for vision processing. You can talk about this part. So now we'll get into the vision.
Well, we use saturation and value to pick up on a certain color.
So what is the difference between hue, saturation, and value?
Hue is the color, saturation, hue is the color, saturation is the amount, like the transparency, and then value
How bright?
is how bright it is.
Yep.
So you used grit when we did this?
Yeah, so in grip, you have to define your ranges. Okay. Yeah. So you define your ranges of your HSV values, and then you can focus on specific ranges of colors. Yeah. Okay. So here's I think I included grip on that flash drive, but here's the link to it. The FRC Screen Steps has a really good, it's a pretty good tutorial on grip and what it does. So that's a pretty good thing to look at. So let's launch grip. Yeah, so this is the one to check. Okay. I don't know. There you go. Okay. So, first thing is you need a source. So you need the webcam as the source. Okay. And you can actually have multiple webcams. Pick 0 because that's the default webcam. Okay. So now it shows the webcam, and then if you want to show it on the screen, I think you just click this one. Okay, so that shows the webcam. Okay. So now what we want to do is we want to add a filter. So HSV threshold. So this is where you add the threshold, and then you just drop it in. And then you have to drag the output of here and put it into the input of the filter. Okay. So now hide this image here, and then show this one. Scroll down and show that one. No problem. Okay, so now it's showing everything because we're filtering. No, put it back on. There. Now change your view now. Okay? So now, if I'm looking for a certain color, I can narrow it down. Okay? So let's try to look for this orange object. Okay, so start. Get it so that it's white. Yeah. Start with the other side. Okay, now hit over and then bring it up a little bit. close with the filters. But then what you want to do is, if you have this now, you then might want to look for a specific shape. Okay? So now, yeah, put contour in. So if you filter it to this point, you got to drag the output from there. Now hide the one. Okay, so now see, this only shows the contour. Okay? Now I have a nice contour of my shape. And if that matches the pattern I'm looking for, I can use that as a target. Okay? So, and this runs in real time, and we're able to get like, I think I've seen, at least on some of our phones, like up to 18 frames per second. So it processes pretty quickly. Okay? Now, once you have this contour, what we're looking at is only sending this contour back to the driver station. This is a lot less data to send than the whole image. Okay? So then you can basically narrow it down and only show where you're at on the field or where the target is. Okay? So if everybody has grip, try running grip on your laptop. And it will, by default, you can use your web camera, or if you have a USB camera, you can plug that in and play around with it. Okay.
Yeah, watch out for the cord there.
Yep. Okay, so then we code, we do our own coding, and then the values so you're just plugging in the code. I'm taking these values and putting them into the code. Cam and use it as an input for the dashboard. And this is running OpenCV on it. Okay. So if you get a U shape that's the right size and color, it will try and pick it up as a target. Okay.
So the data that you're pulling back,
This, it depends on which option I pick.
Yeah.
So if I use robo wheel, yeah, it pulls back and forth. If I program this side,
so it's effectively a standalone program.
Yeah.
And then you're pulling data back into it via network.
yeah. So you can, so there's code here for doing the target tracking. Okay. This project has a couple of dependencies on OpenCV. Okay, so it's probably not going to work right out of the box. I can probably put together some instructions on how to make it set up so it works. But there's a lot of tutorials out there on OpenCV, so it'd be pretty easy to write a little test program in OpenCV to attach to the USB camera and then show a screen. I have some of those test programs. I'll probably email something out if we have everyone's email.
I have a list. If you didn't put your email on here, be sure you give it to me if you want stuff,
And make sure it's legible.
Yep. examples of doing the vision. Now, this is the code. So this is OpenCV code that goes through and does that filtering and everything. And what we do is we look for, this is the main code, okay? So what it does is it takes the image coming in, it has to convert it to the right format for OpenCV. And then what we do is we do a in range. And that's what that HSV filter and grip was. In code, it's just one line. So it's really not, it's, you know, you can use a tool to figure out the right values, and then you can put one line of code in for it to do that filtering, okay? So what it does is it basically says, if I'm in that range of that green lower bound and that green upper bound for the HSV value, then it will send that data out to the next output. And then there's a process in OpenCV where you can dilate. So dilate, what that does is if you have a little circle, it might fill in holes or make it a little bit larger, okay? It's like kind of looking at the sun, it dilates your eyes. So it opens that up. And then the next step is finding the contours. So we find the contours, and then we draw the contours on the screen. And then we basically, we go look at the contours and iterate through them and see if they're a real target. So we have some more logic in here to check the rectangles, and then we make sure there's not a rectangle, there's a rectangle within a rectangle, and that does our checking to make sure it's a real target. So there's some logic in here to do that. But so once you found the target, it finds the X and Y for the center of it, and then it basically does some drawing, some overlay drawing for circles and lines. When it sees the target, it turns it green, things like that. So it's definitely some work, some logic in there, but and then out of that, we basically get our heading, and then we adjust our heading. Okay. So now we had a naming convention on how we wrote our heading values to Smart Dashboard. So we could write our data to Smart Dashboard here, and then it will get picked up by the council. So I was going to show one thing real quick. If I run my dashboard, and if I run a Smart Dashboard console, so I can go into WPI Live and run the outline viewer, and I can start a new Smart Dashboard on localhost. Well, maybe. Yeah, I'll figure that out. Maybe. Okay, so this starts a server, and then we'll try starting a client. That's what we need to do. Yeah, all right.
It's on the side of the screen. Behind your taskbar on the side, you can see the glow.
Yeah. hiding. So now this is where you can add values. So if I actually go and look at my dashboard connects to the smart dashboard, but I think it has to know the robot IP address to connect to.
Yeah, registered,
Yep, so what we have is we have our FRC RoboReal address, but then I have it set so we can test it with localhost. So if we rerun our dashboard, connect it to localhost, and then if we write a value, we'll see if this works. Okay, it just changed our value on our dashboard. Okay, so if everybody can see it's at 120 here. So now if I change it to 90, it changed it to 90. Okay, so this shows how the dashboard is listening to the network table. So the robot is typically writing to this, but I can simulate doing that by just using this the smart dashboard tool. Okay. So when we run when we're running the robot, you can go smart dashboard and see all those variables show up. That would show up on the dashboard. That works quite well. Okay. Any questions on that? Okay. All right. So I think we have, talked about grid, we talked about that. OpenCV, we talked about that. Kind of the strategy for doing your targets, you know, making sure it fits the right shape.
So question for you.
Yes.
When you're working with an office, we work with a camera, and you identify that it's an object, you know, needs to move to the right. How are you signaling that back to the robot?
So we're looking at, there's two, right now I would do it with smart dashboard. I would write a variable to smart dashboard, then RoboReal can read it, okay, in my Java program. What we do is we use like a frame count so that you know when you get a new frame in. So you don't want to constantly look at the image and try to go adjust the image because it could be old.
Yeah.
So we use a frame count to tell that it's a new image. And then every time you get a new frame in, then you make your adjusting to your gyro head. And then, because all you need is, if things work perfect, all you need is one snapshot, and you need your current heading and the heading to the target, and you should be able to calculate the exact angle you need to go.
Did you guys, do you update your heading, desired heading on every frame? Or do you actually move and then recheck after you've done like the full run?
No, we do it on every frame.
Okay.
Yeah, so every frame I get back, I calculate my angle, and then I adjust my target heading.
But are you doing all the calculating on the phone, right?
Well, that's for FTC. On this, we were doing the calculations on the driver station for FRC. But the goal is, I have a couple slides, the goal for next year is to create an onboard module so that we can do it onboard. So we get rid of that delay. Okay. All right, so the next topic was the target tracking. I don't know if you want to take a break or go through this real quick, and then maybe get back to some of the coding. Like I was saying with the target tracking, we can do the angles, right? We can figure out the distance to your object based on the size. All right. Just like here, we have a lot of variables where we have the x and the y, and we know the width, so we can figure out how far away we are from the beacon. We can do some calculations of based on the number of pixels, how wide is the target, so we can figure out how far away we are. Okay. So that's kind of some of the work we did. So what we're thinking for next year is, this will be a module, separate module, a Raspberry Pi, hooked up to 2, maybe even 3 USB cameras. And then we hook that through Ethernet up to the router on the robot, and then we can feed the data to the RoboReel and the dashboard. And the key to feeding into the dashboard is we just feed those contours, so we're not sending a lot of data to the dashboard. And then basically we know when it's on target, and then hopefully we get a fast enough frame rate for that. Okay. And then, you know, Raspberry Pi, multiple webcams, WebSockets, and doing the communication back and forth. So that's some of the work we're looking at. So we're looking at it now, and if there's any teams interested that want to kind of beta test this with us, we'd be glad to work with them.
Yeah, we're actually looking at doing something very similar.
Okay. Yeah, so if you guys want to think about collaborating or working through anything, because we have OpenCV running on the Raspberry Pi, we have that working, we have the network communication working.
Yeah, I've got us a Raspberry Pi 3.
Yep.
And we just with an embedded cam.
Yeah. Oh, okay, you got the embedded cam.
Right. And we were gonna try to work with that and then actually have it signal back. I was thinking using, like we were talking about, network communications back to the RoboReel.
Yep.
I hadn't quite decided whether we should be going with like a standard network protocol and just have the Raspberry Pi stream the information, so basically it processes the frames as fast as it needs to.
Yep. Yep.
And then it would just, every time it ran through a frame, it would send a signal and say, to the left, to the right, up,
Yeah.
down.
Yeah.
And basically we sent that, then we could parse that out in the RoboReel.
Yeah.
And then use that to effectively, as if the user was driving.
Yep. Yep.
Last year, we did effectively that. Our OpenCV code was written in C, or C++,
Okay.
not Java.
Okay.
We wrapped it in a C library called Mongoose, which is a HTTP server.
Okay.
And that way we could test it on the driver station, or we made HTTP GET calls against the Pi to get back just the raw data.
Okay.
And then we had a different URL that we didn't use like during the match or anything,
Yeah.
that would give us a calibration view and an MJPEG
Okay.
stream.
Okay.
It had a lot of latency when we did that,
Yeah.
but if you just were grabbing the GET to get the targeting information, it was pretty quick.
So you were
Yeah.
basically running a web server function.
On the Pi. A few things to be aware of. One, like the best way to tune a camera is to like grab your exposure and drag it all the way down.
Yeah. Yep.
The controlling your camera can be a bit of a trick on the Pi.
Yeah.
A big hint I can give you there that we found not until after the season ended. V4L, the video for Linux.
Okay.
There's packages in the Raspbian.
Yeah.
It has a command line utility that'll control most cameras. The
Yeah.
OpenCV support for,
They don't
work worth a darn.
No.
But the video for Linux packages have a little command line utility, so you can set it up so when it boots, you find all your cameras and
Yep.
drag the exposure down to 0, basically.
Exactly. Okay.
That's a huge thing, and not knowing how to do that was a huge hindrance to us, so that was a
Yeah.
big win.
Because you need that exposure.
You need to, yeah, if you,
down all
otherwise
way.
the lighting kills you. We had
Exactly.
games where it was spot on, or we'd take it to the practice field, I mean, just through the target, we'd go on the field and nothing worked. But yeah, once we figured out how to do the exposure correctly on the Pi, that was a huge advantage. And then just FYI, be careful, most of the time it works, but the MDNS stuff for finding the Pi, sometimes, I don't know if really I think we only had one time it happened, but we had one match where the FMS or something screwed with the MDNS, and so we had called our Pi vision.local. And it worked.
Okay.
except for one match where it didn't, and we got no reason or rhyme why it couldn't, but we could go through the logs and see, oh, that machine doesn't exist, I don't know.
Yeah.
And the Pi was on, and it logged all the data, so we knew it was running and working,
Yep.
but the Rio never saw it.
You didn't static IP the Pi?
Like I said, we used MDNS for everything, now that may
I
have been.
won't ever use that.
So, as a CSA last year, anybody telling you to not do static IP is nuts.
Exactly, yeah.
But, yeah, so probably static IPs are safer, but, yeah, as long as you use and on the machine, it doesn't matter. One other little thing we did run into, just like an operational thing, don't forget the radios only have 2 Ethernet ports on them. And if you're doing tethered testing, you can either get a really long USB cable or like a real cheap hub to like either carry around on your driver's station or something, because it does become an issue. Because you got your Pi hooked into the radio, your Rio's in the radio, you're out of ports.
You know, they had to switch to the little one with only 2 ports.
Yeah, I mean, it's not a big deal, but if you don't think about it, you get to your first competition and you're like,
oh crap.
because you've been testing wirelessly all the time in your lab.
Yeah.
Well, we thought about adding a network hub. That was one of the reasons why I've also speculated instead of using like network calls, use digital I/O interfaces between the Raspberry Pi and the Rio.
Yeah, you could.
And effectively drive the signaling left on one interface.
Yeah, through a digital I/O.
You could.
You could.
The big advantage of doing it all with network stuff is it's a lot easier to test off board with the Pi sitting next to your computer.
Yeah.
You fire up a web server and you're off to the races.
Exactly. Yeah, so we're actually looking at we're doing this in another project. We're doing WebSockets between Raspberry Pis.
WebSockets.
Yeah, because they're fast. You do the HTTP to initialize and then WebSockets. You can publish, subscribe.
Yeah.
So that's
In
it.
years previous, we had done off-board before. We used UDP
Okay.
packets, and we just
Yeah.
fired them
Yeah.
constantly. Whenever we had it, we fired them. If the Rio got them, they got them. If they didn't, it
Okay.
didn't. And that worked really well, actually,
Yeah.
better than the web server did. It was
Oh,
a
yeah.
little harder to debug, but it worked really well. And then one last thing, if everybody hasn't noticed, Grip 1.5 is more or less out, I think, and it has a full code generator in it.
Okay.
So you put up your, you build your Git script, and then you can export the code in Java, C++, or Python.
Okay.
It's not perfect, needs a little cleanup when it's done,
Yeah.
but it's,
Yeah. It'd be a good start.
it gives you, for the kids, it gives them a nice framework on how to program an OpenCV for the first time, and all that sort of thing, so.
That's good. Yeah, because at Worlds, a couple teams were doing presentations as well, and they were using an Android phone,
Yeah.
and they were using a USB connection between the phone and the Rio. But then you have to get into USB coding and all that stuff.
Yeah, they were using, the Android Developer Bridge, I think.
Yeah, ADB. Yeah, they were using ADB, so, which is another option, because you can run TCP/IP over
Yep.
ADB.
And the phones tend to have a lot faster processors than a Pi does, too.
Yeah.
I mean, you don't even have to spend a lot of money to get a phone with 5-10 times the processing power of a Pi.
Yep.
$20, it's not easy.
Exactly. Well, we're getting $20 ZTE coins for FTC.
Exactly.
Yeah, they have quad processors in them, so.
Mine's what,
It's a quad processor now, but it's,
Pi 3 is better,
yeah.
but, yeah.
It's a
the
32
older
bit,
ones
right?
are-
Essentially, it's an ARM V7.
Okay, yeah, okay, it's the Arduinos I'm thinking, most of the Arduinos are the 8-bit ones,
Yeah.
that's right.
Yeah, the Arduinos are a lot less. That's good. So, yeah, so that's, pretty much what we have. Any questions? Anybody have anything there? Did the coding help a little bit, the state machines and that stuff? That's good. Good. So, that's, live and breathe by state machines, that's what we do.
Everything we do is stage,
Yep.
almost everything.
Yep. We do state machines in Teleop for managing the state of like your arms and things like that. Just-
Especially when we have like, because, last year on a robot, we had an arm, and then we had an angle on a shooter too. So we made that into a state machine for teleop, so we're able to control it.
Yeah.
What are the
I guess, what are the differences between command and state? Like, what is better about the state that would?
I wouldn't say one's better than the other, I'd just say they're different. Command-based program gives you behavior, and you can implement the same thing in a state machine. It's just really your preference or how you like to code it. At least I always like to understand how the whole framework works, so I know how all the code works. For a framework, you're living by somebody else's code, and I'd rather know how it all works. That's really the only difference. Yeah.
Just so all of you know, before you drive home, please be careful. Apparently they've shut down I-75 back Holly. There's another big party going south, might have a lane open, another big pile up. So there's snow outside, be careful.
Works best with vision processing, or any tips there for what they should be looking at?
Well, we did the, all of our stuff was CAN. The CAN bus, and they were CAN, Talon.
Yeah,
the SRSs?
Yes.
Yeah, those are nice.
They worked really nice.
Yeah, they're talented.
Our code was pretty simple. We tried to use they had some feedback controls with the CAN Talon. We opted not to go that way, because the only thing I can say is we tried they had these absolute position sensors, and all it took was one jitter, and it would throw their PID loop into a spin, and it would go crazy. So we got rid of all of the absolute.
What kind of absolute position were you using?
There's one that Talon. There was an absolute position sensor with a little magnet and then a little outer piece to it.
Oh, yeah,
that would feed right into the Talon. If that thing's not
I hate
perfect,
them, but
I will never use those
Why?
again.
strange things happen. We were using them just for velocity, and I don't know, you can feed stuff into the Talons like with the optical sensors, feed it in, and they worked every single time, but when we went to those magnetic ones.
Yeah, I would not recommend those.
Yeah.
You don't like the magnetic ones?
Oh, they killed us.
I had it, he's right, we had,
No,
speaking of killing somebody,
the person who put my.
we had one, we were using one to control an arm on our robot, and every now and then, something happened, and it would go hard over.
Yeah.
Yeah, that's
Unfortunately-
exactly what ours did. We had a huge arm, and it just go phew, and everybody's like, what the heck?
Yeah,
Like,
well,
not me.
unfortunately, we were near the edge of the field, and we almost got the head referee.
Really?
He disabled us.
Yeah.
You have a bad robot card, huh?
Yeah, we were disabled.
Yep.
They, and rightly so.
Yeah.
Now, those are by far their
Yeah.
least
Yeah,
favorite.
those
I
are
don't
those
know
are
anything
my
about
least
those
favorite
things.
Yeah, that's my least favorite sensor, followed by the gyro.
That and gyro.
Have you guys looked at all at the new integrated devices that have gyros and?
Oh, and like the nav apps and things like
Yeah.
that. We haven't got one yet, but we're probably gonna try one out. I've heard they work a lot better.
We've used the NavX for 2 years in a row. We found them to be quite accurate and reliable. I mean, you do have to be careful, because of the way it mounts, you want to make sure you mount your robo reel more or less flat and in the center of your robot to be most useful. You know, a separate sensor is a little more flexible,
Yeah.
but we found it to be really reliable.
Does the NavX plug directly into the robot?
Yeah, it fits right into the expansion port, and it also has breakouts for all the other stuff on that MXP port.
Yeah, those data, they stick on the shaft. The outer piece has to be perfect, otherwise any of those.
Yeah, you gotta be like a millimeter off the shaft.
Exactly.
Yep.
Yeah, we were actually looking at 3D printing a mount.
Yeah.
And then you basically having a thin film in between them.
Yeah.
Yeah.
We had trouble with ours, and the ones we were using came directly from across the road, and they're mounted inside They were mounted as part of the transmission.
Oh, really?
Yeah, and they. and
So
they
that was
still
part
have
of the
brain
standard
injury.
build transmission? Oh, okay, all right.
And I know what was going on, but we had some strange things happen.
Yeah, see, they're doing feedback controls and they're not filtering that signal, because I logged the data, every once in a while there'd be a jitter. And they weren't filtering it out, and I don't know what they were doing, so I said, we're not using their PID.
Did you talk to the Crossroads guys?
Yeah.
So they say they just take it raw, because we've looked at it, we actually played with, now, we didn't have it on our drivetrain, we had the talons on our shooter,
Yeah.
and we were just trying to get consistent velocity, and we
Okay.
had, we're software guys, but we had
Yeah.
the box, the gearing box, and it had an integrated, sensor in it.
Encoder.
It had the encoder integrated into it, and same thing, I monitoring the data, we'd see these bizarre, weird spikes,
Yep.
and if you filtered it, it was no big deal.
Yeah.
Yeah.
But if they're taking that data raw, like a D term is just gonna die on that, right?
Exactly.
Because
Yeah.
they eat air, they magnify air up off the, off the scale, so.
Yep, yep. Yeah, same thing. So, that's why we like plotting the data, so you can see that.
Yeah.
And what is it causing the problem? And when you have a closed loop subsystem like that, you have no data, you can't
Right.
look at it.
Yeah, no, but it's tempting because it runs at what, like 1,000 cycles a second
Oh,
or
yeah.
something crazy,
Yeah.
and so it should theoretically be very responsive.
Yes.
And it's on our list of things to test. So.
Yeah. Yep. That's about it. But the vision stuff is fun to play with. It's good to learn because there's going to be a lot of jobs in the future using vision.
Oh, yeah.
Yeah, you're a town star.
Yep.
You good, you do an hour short.
Yep.
Why are you?
Yeah.